Hello hackers, and welcome to another update on what the heck is going on with this, the hack project or the HEC project. And believe me when I say there's a lot to unpack here. And first things first, if you have not seen it, well, this big red thing here is called the Vera, the Versatile Embedded Retro Adapter, which is the fancy name for the graphics card for the Commander X16. And it is working. It's such an easy thing to say, but it actually took me a long time to get it to work. Basically, I have to put it on, take it off, put it on, take it off, and hook it up to an Arduino and code up some timing values in Arduino IDE and try it out just to find out that there's a timing bug in the firmware of the Vera. So I did a lot of back and forth with one of the code designers, and we haven't pinpointed like which line that caused the bug, but we have a new version of the firmware that fixed this problem, and now it works fine. Next, you have this dangling thing here. This is the EEPROM Emulator NG Special Edition. As you can see, there are some bodges going on the back. I put a diode here, I put some pins here, and you cannot see it, but I actually soldered some pins over here. And that is all to bring the power-ish that didn't work very well, but it worked well enough, and reset to this connector. And they're not in their original intended position on the ROM emulator NG, but all of these, in addition to some of the bodges that I did here, means that I can update the firmware really quickly. If you've seen my stream the day before yesterday, you can see me just writing some code and pressing Ctrl-Shift-B, and after a while, it's updated. This supercharges the development of the firmware. Let me tell you, before that, I have to write the code, assemble it, take the EEPROM out, put it in the programmer, program it, take it out of the program, put it back in, and test the code. And if it doesn't work, because of course it doesn't, or if I need to add some new features, I would write some code, take it out, program it, do all the stuff over and over again. Now it's just literally a key combo. And because of the mod I did, if I plug this in, plug power to this board, without plugging in the PC, this still works. This thing functions exactly the same as a ROM. So that's super great, but this is going. In the next generation of boards, this is going, because next generation will not be a prototype. We will get to that later. And the third thing I want you to focus on is the LED, the 7-segment LED here. This 7-segment LED is one of the keystones, I say, of early design debug process, because this LED works without the CPU having access to any other hardware. Like, this LED would probably work without the RAM working, without the paging circuit working, without the interrupt circuit working, probably without 90% of the board working. And it's super helpful. However, it currently has a bug that prevents this LED from displaying value while the board is running application code. If it's like in a debug mode, then I can use the LED freely. But I would say currently it has served its purpose. and I just use it occasionally because I've got the video output on the Vero working, and I've got much more detailed debug information from the VGA port. But I will still include this in the future revision because I intend this to output some kind of post code. So just in case your board does not work, you are not debugging with like eyes covered up in a darkness, something like that. You have a clear indication of which part the post has gone to, and probably that will give you an indication of like which part of the board is causing you trouble. Moving on, let's talk about all the peripherals first. This is the HEC HT6542 6542B, and this is the KMI, or the keyboard mouse controller, keyboard mouse interface. It basically interfaces with the PS2 port. I have PS2 keyboard, I have PS2 mouse, and they both work. I haven't tested the mouse yet, but if this works, then everything works. The PS2 works and the translation works. Also, this thing drives the NES controller port. Yeah, this thing has an NES controller port, and it is interfaced with the PS2 controller. I will make a video on how I did it. It's super interesting. Wait for that. Subscribe. But for now, the biggest thing is that it works. And next to it is another working port, and that's also a controller port, but this is an Atari/Commodore style controller port. Like this one. It has two buttons, but two buttons are both connected to fire. And some of you might ask, oh gee, Andy, why do you put like two types of different controller ports? Wouldn't that be a nightmare for game programmers? It's like each time a game would need to ask the users, like, oh, do you have an NES controller, or do you have a Atari controller? And the game would have like a controller reading code for both. Well, the answer is no. And because the HEC has a protected mode, and that's its main feature, which means all the controller interfacing is handled by the system. If the game does not need extra buttons, for example, the B button or the select or start on an NES controller, it can treat any controller like an Atari controller. So it will just ask the system, is the fire button on the controller pressed down? And the system will read the appropriate controller port and say, well, okay, it's pressed down or it's not. And that's all the peripheral part. They are all working. That's such a relief, because this board is my first full PCB design, and it's so big. I often say to people, it's like, this should not be your first PCB design, and this is my first PCB design. So yeah. And let's move on to the RAM part. The RAM part works. The paging circuit works. The protection circuit almost works. The interrupt circuit almost works. The issue with both is that because the Z80 has a refresh cycle after the M1 cycle, the protection circuit will take the refresh address instead of the instruction address and ask about the paging circuit whether that address contains a valid instruction. It's not the refresh address, it's actually, because it's the upper 8-bit of the address bus, is actually the interrupt page address. But it's a completely different issue, and also because the LED is using the interrupt page address as the debug output, it prevents me to use this as a debug output if the interrupts are enabled. But if I'm debugging it, I'll probably have the interrupts disabled to prevent external hardware from just interrupting the debug process. So it's not such a big deal, but in the next revision of the PCB, I've got this bug patched. Moving along, we have our final botch here. It's the screen wires. You probably cannot see it very clearly, but I have two green wires. These are to botch a really just stupid wiring bug that I had in the design. Basically, I wired up the wrong pin to the CPU NMI signal, so that the CPU just constantly being non-maskable interrupt by the non-maskable interrupt circuit. So whenever it comes out of non-maskable interrupt, it will be immediately throw back to non-maskable interrupt, and you go back and forth and back and forth and back and forth and like that. And this just rewires. This just requires some rewiring, and it just works. But I mean, although I've said this thing takes a long time, actually the Vera takes about more than a week and a half to get working. I know a lot of people still have the questions like, why is it taking so long? I know a lot of people want like a full kit or like a second generation or something. And I promise you, those are in the works. I have a second generation board. From now on, I'll call the second revision board, because the second revision will still be a fully dip version. And if I call it the second generation, I think people will mistaken it with like the X16 second generation board, which is like fully surface mounted and cost reduced and stuff. There will be a second generation, like in the X16 sense of the HEC project. I'm in the early stage of designing one. It will have surface mounted components. It will have maybe some programmable logic devices to replace some of the TTL gates. It may have a fully TTL version. I haven't like decided on that yet. And there will be a third generation, which is highly programmable logic, if not fully just one big FPGA. But that aside, before I can move along with any of that, what I've been doing these days is designing interfaces. For example, if you've seen my live stream a few days ago, I have got like trees to display on the screen. And from that point, I can actually do a lot of things. I can animate those trees. I can move them around using scrolling registers. I can just change the palette so that the trees change color. Like, I can do a lot of those things. However, that's kind of not my priority right now. I kind of have like a different set of concerns than other Z80 microcomputer, like microcomputer, like single board computer projects. Normal Z80 single board computer projects, they have, I will say, hardware design, and after the hardware design, I think most people would just get CPM working. Like after they've got the equivalent of this, the first thing they will say, oh, well, I'm going to write a BIOS and I'm going to get CPM working. But what I've observed is a lot of these projects that once you get CPM working on this, the next thing is like, what? Because CPM is not a very powerful operating system. You can get some of the game working if you have like a basic TTL driver. You can get like text adventures working. If you have some fancy ANSI command set interpretation, you can get some of the graphics game working. But that's about all you can do with CPM. So people would usually just release their hardware and try to build a community and try to have people like programming in assembly language and use their maybe graphics hardware, maybe their sound hardware and stuff. But I don't want to get stuck with CP/M, so I have designed an operating system that would take the full advantage of the HEC. And one thing I want to mention is that another thing that happens between this and the last update is VCF Southwest. And I've done a video on the X16 presentation during the Vintage Computer Festival. But another thing I want to mention is that I also watched the porting OS 9 to the Phoenix computer project, which is kind of the Phoenix update video. And I find an interesting trend, like there are people, I don't know if it's the same person or different people, asking in those videos about operating systems. And the trend is that when people build a computer, people start asking like, what's the operating system for it? And when they got the answer, the next question is, does it have multitasking? And when the answer is also yes to that, it will be, does the system protect the hardware registers? And or does the system have a graphical user interface? And I'm glad to say that those four things are unambiguously in the roadmap for the HEC. So stay tuned for it. But before I can get to any of those, I need a robust interface. So what I've been designing like most of the time these weeks actually is trying to come up with an interface, not only a programming interface but a hardware interface as well. As you can see, the expansion bus on this prototype board has not been populated, and that's because they contain not a bug but a design change. They currently have the X16 style audio, but it's not the X16 style audio input, but it's actually an audio output. But it has the audio on it. I ultimately decided to change that to I2C bus because I think more peripherals needs I2C than a audio signal. And all of these changes are very hard to make. I spent a lot of time making design decisions like this because I want my bus connector to be as versatile as possible while being as minimal as possible. And that's just the hardware. And software, turns out, is even harder. And that's mostly boiled down to I'm working on an 8-bit computer. I will give you an example. The HEC motherboard use a set, not this motherboard, the computer use a set of restart instructions on the Z80 to communicate between the user program and the system. The restart instruction is kind of like the DOS interrupt 21, if you know a lot about DOS programming, or just the Linux syscall. And the problem is that this is not how 8-bit computer usually work. People are used to programming 8-bit computer by directly writing to registers and sometimes even counting the CPU cycles to produce specific effects on the screen and stuff. And that kind of sets an expectation of like how good a Z80 or 6502 program will look and sound. And when I suddenly have this type of overhead of constantly going into a system mode or kernel mode and going back to user mode, and each time I do that transition, I need to spend some cycles on that, it quickly degrades the performance of the program. Even though the CPU runs at much higher clock speed, it may end up still being slower than an MSX. And I know about most people, it's like most people who are into this like the games. They like to see cool demos. They don't actually care about, okay, how is this implemented, like the nitty-gritty detail about like the communication being done in the motherboard and stuff. So I have to deliver on that effect. And that requires me to be very smart in choosing like which functions to implement in the system routines, the kernel routines, so that I can take over as much as possible from the user side or the programmer side without limiting the creativity of the programs, without limiting the versatility of the entire interface. And that difficulty is compounded by the fact that 64K is really not enough for anyone. When I'm designing this, I constantly run into issue that I just need like a full 64K of RAM just to store a table, just to store a lookup table or something. And that's just not viable if I'm designing with a computer with a 64 kilobytes of address space. If I need that lookup table, I would be constantly swapping banks of memory, or in this case, swapping pages of memory. That is just not viable. I have to conserve memory as much as possible, but I also have to design in the fact that most programs, most drivers would require more than 64K of memory. And that's more difficult, I would argue, than writing a driver for something like a 386 or just a 32-bit microcontroller. And that's just comes down to the sheer fact that the 32-bit CPUs have 4 gigabytes of address space. If you are programming on a 32-bit computer, usually when you pass down a pointer to a function, to a driver, it can just load data from that pointer, no problem. But for example, if you're passing a pointer that points to maybe some graphics data you want to show on the screen to a function that calls the driver of the graphics card, well, the graphics card driver says, well, okay, pass me the data. And the graphics driver also says, I need some more memory to load that data to the graphics card. Maybe it has some information about like the address map on the VRAM and stuff. Doesn't matter. And the graphics driver says to the system, hey system, can you bring in some more memory for me? And the system says, well, all right. And then it swaps the banks of memory. And boom, suddenly you have garbage on your screen. And the whole reason behind that is that the memory that your pointer is pointing to, that is your graphics memory, the thing you want to show on screen, might be switched by the system and replaced with whatever the graphics card driver needs. And I have to design a system to prevent that from happening. And on top of that, I have to design a system that can multitask. This is another thing that none of the 8-bit systems need to worry about, and all of the systems that need to worry about that are not 8-bit. I know a few 8-bit computers can do multitasking, but those multitasking are usually cooperative. Basically, the different programs, they know the existence of each other, and they know how to not step on each other's foot. But the HEC is designed in a way that programs that have no idea about the existence of each other would work together, and they would not step on each other's foot. And on top of that, I made a 400 IQ decision decision that the HEC would use dynamically linked libraries. And what that means is that the programmer don't have to write duplicated code. If someone has written a code for you, you can just add that to the dependency of your program, and that code does not even exist in your program file. It will be brought in by the system during load time. And that also means that if there is some bug found in that common program, you don't have to update each and every of your games and application that use that piece of code. You just have to update the library file. Super simple. But it just turbocharges the complexity of the loader, which is the part of the operating system that's in charge of loading the program into memory, because it has load multiple programs into different segments of memory and change some values within those programs so that the program knows where they are and where each other are, so that these programs that don't know about each other again will be kind of introduced to each other and have some kind of agreement that they would not step on each other's foot. And that's on top of this whole happy mess, not stepping on the foot of another process, which is another big happy mess. I'm sweating. I've been explaining. I've been trying to explain this like maybe for half an hour now, and I think I still cannot fully express the complexity of this thing. So I would end the video on not a high note, but something more cheerful. Let's talk about maybe the long-term prospects of the project. I've already stated there will be a second generation unit, there will be a third generation, maybe there is a fourth generation unit. But I also want to have a 65V 2 version. And that basically comes down to the same expansion bus. Basically, don't hold me to that. This is in even earlier design stage. I've come up with some kind of memory map and stuff, and that's it. But what's cool about this is that it will still use the same expansion bus, which means whatever car you design for this expansion slot will just directly goes into that machine and it will work. And next thing is that I found this interesting chip made by FTDI, and that chip would connect to a computer with a USB cable, and it has this function called an MCU emulator. It does not actually emulate the function of an MCU, but it has an Z80-like interface, which means it has the read and write signal and a parallel 8-bit data bus and all kinds of stuff to it. Which means I want to design a board that's kind of like the IBM I/O expansion unit, but instead of plugging into a PC, the IBM one, I'll plug into a modern computer and give you a few HEC compatible expansion slots. And that makes debugging the cards so much simpler. So if you are designing like a graphics card, if you are designing a sound card, if you're designing something, you don't even have to buy this board. You can just buy the adapter and plug it into your PC and off you go. And that's also super helpful for people who want to, for example, write music. As I've got quite a few different kinds of sound cards. The ones that use SID, ones that use like the SN76489, the ones that use like the AY3 sound chip, the one that use Yamaha, OPL, OPL2, like OPM, all kinds of stuff. And if you want, you can just populate expansion board like with like 8 sound cards or something and plug that to your PC and just go wild with it. And you can just listen to FM sound coming from one channel and PSG sound coming from another channel, and you can compose using probably a PC program, and you throw it onto that card, and you probably just output like a VGM file, and you can play it on a real machine. And I've also come up with some interesting chassis designs just in my head. I want like the box for the HEC to be like an Amiga 1000 style. You've seen that? It's just a beige box, no fancy like RGB, no crazy design like the modern PCs. None of that. It's just a box with a 3.5-inch floppy disk slot on one side. And I want that box to be able to be flipped on its side and stand vertically, kind of like some earlier PCs, kind of like the Atari Falcon design that's later used as the PlayStation 2 chassis. And I've got a smaller design that's kind of the same shape but shrink down with the floppy disk port replaced by a compact flash card port. So it's like smaller with less expansion slots, but it's more compact. That's probably for the 2nd generation unit. And the 3rd and 4th generation unit is another shrink of that, and is again the same shape, that same exterior, but replace the compact flash card slot with the SD card slot. So it's kind of like a C64 mini of itself or something. But I guess that is the end of all the fun things I want to talk about this computer. I'm Andy, and I will see you in my next video. It doesn't matter. It will just ask the system, oh, is the controller, for example, pressing with like the fire button pressed down? Does the fire button on the controller? It will just ask this.